Thank you for attending today's SBCA webinar, Designing with Top Chord Bearing Floor Trusses. When metal plate connected wood floor trusses are being considered for specification in a construction of a project, there can be many questions about if and or how these trusses can be used in certain applications. Floor trusses are highly adaptable structural framing products, but it can be difficult for a building designer to know how a floor truss can be designed and when it can be used to solve a particular framing challenge. This presentation is going to briefly talk about floor trusses in general, and then focus specifically on top chord bearing trusses and the benefits these unique framing products can bring to building designers. This is the 7th in a series of webinars aimed at informing building designers, whether they're architects, engineers, or others in the design community, on aspects of the component manufacturing industry. The overall goal of this series is to provide structural component design guidance, as well as provide perspectives on what today's component manufacturing industry is capable of, and also explore how the component manufacturing industry can be an effective partner with building designers in ways that will make their lives easier and or make them heroes in the eyes of their customers. And because the audience for any one of these presentations may include design professionals from many different disciplines with varying levels of expertise and who work on anything from single family to multifamily or light commercial, most of my observations today will remain at the 30,000-foot view. My name is Sean Shields. I'm the Director of Marketing for SBCA. I've been with the association for over 20 years and will be bringing to bear my experience talking with component manufacturers across the United States throughout this presentation. My goal in today's presentation and all subsequent webinars in this series is to share the industry's best practices and promote the industry's expertise and capabilities. Here's a brief summary of what I will cover in this presentation. I'm going to start by providing just a brief overview of SBCA and its role in the component manufacturing industry. I do this because I want to give everyone on this call a sense for the size of the component manufacturing industry, as well as the role of SBCA within that industry. And then I'll get into some basic terminology regarding floor truss design and how they are manufactured. Then I'll explore some of the benefits that can be achieved through the use of top chord bearing floor trusses. I'll then walk through the recent changes that have been made to top chord bearing floor truss design that will make them even more flexible for building designers. And I'll end the presentation with a discussion on how today's component manufacturer can be a valuable resource to building designers in the building design process. Now, SBCA is the premier trade association for the structural building components industry in North America. With over 40 years of history, SBCA has developed an extensive network that enables it to reach the entire length and breadth of this unique aspect of the construction industry. SBCA has a strong tradition of providing sound engineering and fabrication guidance to its many manufacturing members to help promote their growth and success in the marketplace. However, as the market has matured, SBCA's primary focus has shifted to helping build connections between companies and individuals throughout the industry, whether they're in the same local market or spread across the continent. It's through these relationships that are built. SBCA does this through face-to-face events, virtual events online, and digital communication. SBCA's premier face-to-face event is the annual Building Component Manufacturers Conference, or BCMC, which is traditionally held in the fall. BCMC brings thousands of manufacturers and suppliers together for a week of intense networking, idea sharing, and business transactions. Now, in addition to the BCMC show, SBCA hosts 3 additional face-to-face meetings throughout the year called Open Quarterly Meetings. These meetings are held across the country and offer anyone a more intimate opportunity to build relationships with some of the largest and most forward-thinking component manufacturers in the industry. Finally, SBCA has developed an extensive suite of tools and resources for today's component manufacturer that range from digital quality management software to an extensive library of online training modules. This scatter plot gives you a sense for SBCA's overall membership. This scatter plot shows the over 1,300 component manufacturing facilities located in the United States. Of those dots, 907 of them belong to SBCA member companies. As you can see, these facilities reach every community in the country, allowing builders and building designers to use these products in any project, no matter where they're located in the US. To give a sense of scale, SBCA member facilities sold approximately $9.12 billion in product in 2023, out of an estimated total of $9.31 billion. The last thing I want to say about SBCA is to underscore that it's an inclusive organization that welcomes everyone engaged in the light frame construction industry to get tied into our extensive network of structural component manufacturers and their entire supply chain. There is an infinite number of opportunities for individuals to get involved, meet manufacturers, share ideas, solve problems, receive and offer education, and most importantly, build meaningful business relationships that can transform the way anyone approaches their job and positively alter the trajectory of their business and career. Now, before we get into talking about trusses, I want to quickly mention the standard that governs the design and manufacturing of metal plate connected wood trusses, ANSI TPI 1. This is a consensus-based standard that was first published by the Truss Plate Institute, or TPI, in 1961. The standard is then updated on a very regular basis. The most recent edition of ANSI TPI 1 is 2022. This was approved as an American national standard in December of 2022. And this standard will be incorporated into the 2027 model building codes. For now, most building codes across the US will reference the ANSI TPI 1 2014 standard. That's significant because there are significant changes in the 2022 version that I'm going to go through today that impact the design and application of top chord bearing floor trusses, making them even more versatile than they've been in the past. But I want to note that while the local building code may not specify TPI 1 2022 or specifically reference it, there's nothing stopping a component manufacturer from taking advantage of the new design criteria contained in the 2022 standard by accessing it through their proprietary design software. Okay, so today we're going to focus on a particular type of parallel chord truss. Now, trusses are categorized as parallel chord for use in floor and flat roof applications. These prefabricated wood framing components are a framing alternative to conventional dimensional lumber, which you see on the left, and EWP I-joists, which you see on the right. Now, both of these framing methodologies have their advantages in various applications, but open web floor trusses present an economical and versatile alternative that the other two simply can't achieve as easily. And we're going to talk about how that is so. It may come as a surprise that engineered floor trusses have been on the market since the mid-1950s. However, they have really greatly increased in popularity over just the past decade, again, due to their exceptional strength, durability, some of the many construction advantages they offer, and their reliability. In this presentation, we're going to focus on one type of floor truss, the top chord bearing floor truss. But I want to make sure that everyone who is watching this webinar is starting from the same foundation. So floor systems on a fundamental level and the elements that make them up provide structural support for the internal space of a building. Floor system elements essentially provide stability and absorb the impact of the occupants and the contents of the building. A floor truss is an engineered product designed to carry those floor loads out to bearings. And a truss is manufactured from custom cut components, which are connected using metal connector plates. And floor trusses are typically fabricated from 2x4s or 2x6s, dimensional lumber that are generally installed either at 16 inches, 19.2, or 24 inches on center, depending on the depth and span of those trusses. In floor truss applications, that 2x or 2x6 material is typically used with the wider portion of the board resting on the bearing, or what is known as a 4x2 or 6x2 configuration. In this orientation, truss manufacturers may also produce floor trusses with 2x3s or 2x6s, putting them in the 3x2 or 6x2 orientation. Now, with floor trusses, there are typically two different bearing conditions: bottom chord bearing and top chord bearing. In the bottom chord bearing configuration, which you currently can see on the screen, the bottom chord is used to transfer forces to the truss bearings. The bottom chord typically carries combined tension and bending stresses. Another floor truss configuration is the top chord bearing truss. In this configuration, the top chord of the truss is responsible for transferring forces to the bearing. The top chord then carries the combined tension and bending stresses. But typically, floor truss webs are arranged in a pattern to maximize triangulation of compression and tension forces that allow the truss to span large distances. And it's due to this triangulation, the depth of the floor truss, as well as the strength properties of the wood used in its construction, that play a major role in the distance that a floor truss can span. Also within the truss are perpendicular webs that are used at bearing locations and at chase openings. Over bearing locations, these perpendicular webs allow for efficient transfer of forces directly from bearing walls above the truss into the bearing location. With top chord bearing trusses, there are no perpendicular webs bearing on support structure, just the top chord itself. For chase openings, these rectangular or square openings allow for easier installation of HVAC, mechanicals, plumbing, and electrical infrastructure. But for top chord bearing trusses, these openings can also accommodate interior bearings like pocket beams, like we can see in the construction detail on the right. In every case, bearing area is crucial for floor trusses because it determines how effectively the truss, one, transfers load to the supporting wall or beam, two, prevents crushing of the bearing surfaces, and three, ensures the structural integrity of the entire floor and wall systems. If the bearing area is too small, the concentrated load coming through the truss at the bearing location can exceed the capacity of the wall, leading to potential structural failure. A larger bearing area spreads the load from the truss more evenly across the supporting members, reducing stress at the contact point and minimizing the risk of crushing. The key here is that the truss designers carefully calculate the required bearing area based on the anticipated load on the truss and the strength of the supporting wall materials. Even the grade and species of the wood used for the bearing surface, both of the truss and of the support structure, impact a floor truss's capacity to handle the compressive forces carried through it to the end bearing location. So those are some basics. I mentioned that floor trusses are manufactured in a facility. If pictures speak 1,000 words, hopefully this video will communicate volumes. This is a video clip that gives you a glimpse on how these structural framing elements are assembled. Now, the wood cords and webs are pre-cut using a computerized saw. The saw cuts to the specifications of each individual truss per the truss design drawing. At a floor truss assembly table, as you see here, the pre-cut cords and webs are laid out prior to the application of the metal connector plates. As a result of this process, every joint, as you can see here at the end of the video, is snug and precise, which results in a superior performing product. Now, once all the cords and webs are laid out, The metal connector plates are tacked at the joints to ensure that they don't shift when they are mechanically embedded into the wood. Again, the individual truss design drawings will specify the size, the orientation, and the location of each connector plate. And when all of the metal connector plates are tacked into place, the plates are embedded into the wood to create solid and secure truss joints. You may notice as this roller gantry is going over that the plates are only being embedded on one face of the truss. With this particular machine setup, the truss will be mechanically flipped onto this opposite bay that's open. And then the backside plates will be tacked at the joints, and this roller press will go over the truss again. One of the most important things to note about floor trusses is that they are not standardized products like 2x8s or I-joists. Each truss can be designed and manufactured for specific applications, whether it's to achieve a particular span between bearing locations, or to achieve a particular floor depth, or to incorporate a particular element like a pocket beam or recessed header into the floor system itself. Structural framing products like the top chord bearing truss allow a building designer to achieve additional customization, really anything that they want to achieve for any given project. And I'll give you two great examples, one for multifamily and one for single family construction. So looking at multifamily benefits, if you look specifically at like type 3A typical construction, one of the more significant challenge that building designers face is trying to design exterior wall assemblies with a 2-hour fire rating. One way to avoid using expensive fire-treated LVL, for example, in rim board on the exterior of the floor systems, is to balloon frame the wall up into the floor cavity itself, and then use a top chord bearing truss that'll sit on top of the wall. You know, when you look at projects like the one on the screen, at the scale of projects this size, developers can save then tens of thousands of dollars avoiding the use of this expensive fire-treated LVL, just with a simple conversion into a top chord bearing truss. And this isn't theoretical. Component manufacturers are doing this across the country right now. And there are several developers who have switched to this methodology and swear by it and won't ever go back. On the single family side of things, as baby boomers and others age, one trend that is increasing in popularity, according to NHB studies, is minimizing elevation changes in a home. Top chord bearing trusses can help enable building designers to create zero entry homes, whether that's eliminating steps into the home from exterior openings, or with the addition, with additional design elements like piggybacks, which we'll look at here in a few moments. You can also incorporate drop top chord floor trusses to create zero entries into showers. So again, those are only two quick examples. There are many that top chord bearing trusses allow, but hopefully that gives a sense to building designers that for any given project, there's lots of versatility with this type of framing element. In this next section of the presentation, I want to talk a little bit about designing with top chord bearing trusses. With this condition, the bearing surface contact between the support structure and the bottom of the top chord is critically important. Traditionally, top chord bearing trusses are designed to accommodate a maximum of a 1/2 inch gap between bearing and the first vertical web. This is designed intentionally as a construction tolerance and for the potential application of gypsum for fire protection or fire separation. Now, when a truss designer is designing a top chord bearing truss, they check for several forces: compression perpendicular to grain, bending, shear, rolling shear, and tension perpendicular to grain. These checks are dependent on adequate bearing surface contact. So it's been critical to maintain the expected bending forces in top joints and not exceed that half-inch gap. And that's because the larger that gap at the time of construction, the higher the bending forces then in the top chord. So for example, if after construction there's a 1/2 inch gap, that will double the bending forces going through that joint. Now, depending on conditions, that what seems like even a small change can cause serviceability issues later on in the building's life cycle. I'll give you one instance. Recently, SBCA's technical director, Greg Greenlee, inspected a number of buildings constructed with top chord bearing trusses where the walls had moved out of plane. And this was mainly due to a seismic event. And this had resulted in gaps exceeding 3 inches, again, between the support structure and that first vertical. Now, the buildings didn't collapse, but there was evidence of truss deflection that far exceeded design specifications. And so that's an important factor that needs to be tended to with top chord bearing trusses. In a minute, I'll talk about sort of some of the changes in design criteria that will have an impact on that for sure. Sometimes the building designer may want or need to increase the allowable bending forces at a support structure. And so a truss designer can design a continuous top chord bearing truss with an interior pocket bearing location. The continuous top chord allows for an increase in allowable bending. And as you can see in the detail on the left and in the image on the right, the bottom chord can be removed at that bearing location if needed. Now, sometimes that can be that instead of that being a beam, maybe it's a wall and they want to affix drywall in those areas, then that bottom chord can be eliminated. Here's another detail that sort of shows a benefit of top chord bearing trusses. They can be used to enable building designers to upset a rough opening header and incorporate it into the floor system, particularly like in this particular case for an interior load-bearing wall. Sometimes where you'll see this are entryways into multifamily units from an interior corridor or hallway. In this case, the building designer may want to move that header into the floor to accommodate either a taller door or a window above the door or some other design element. Again, that top chord bearing condition allows the building designer to move the bearing up into the floor system itself and create more design flexibility for that rough opening. Piggyback situations occur in a couple of different ways, but they occur in floor trusses when a designer may seek to maximize the use of an interior support structure that doesn't provide a lot of bearing area. So again, you might have a lot of load going across between the two trusses that you see in the detail on the left. In this case, you have a top chord bearing truss being used to bear onto a bottom chord bearing truss. This design can maximize use of the bearing area on the support structure for the bottom chord truss by lining up the panel point over the bearing location. And then you maximize the bearing for the top chord truss by maintaining or by having it bear on the bottom chord bearing truss, maintaining that maximum half-inch gap to the vertical web. You can see sort of two different details of that here on the screen. Now, I alluded to this earlier about zero entry, and that piggyback detail can also enable zero entry into, let's say, like a shower pan. So, for building designers and developers, design costs are typically saved when there is one basic structural design for the shell and only minor floor plan variations. Design time for the engineer can be reduced as truss designers are deferred to, and the truss manufacturer reduces cost, design changes, and whatnot. Trusses give design professionals the design freedom to incorporate architectural details into individual truss designs, such as the concealed beams that we were looking at. It can also apply to cantilevers, balcony steps, anything. These prefabricated designs reduce framing complexity and simplify installation, which reduces install times themselves. And on the left is, and just as an example, is an installation detail of a flushed shower pan in an I-joist floor system. I don't mean to pick on them, but it's just a detail that was readily available. To complete this particular design, 2 headers have to be installed to run from beam to support the smaller framing elements where the shower pan will go. These 2x interior members are spaced at 12 inches on center and require 14 additional hangers to support all the pieces. As you can imagine, a detail like this takes a significant amount of time and material to frame in the field, much less a lot of expertise to understand exactly how to pull it off. This same framing result can be handled more easily and efficiently with floor trusses by designing additional webs into the truss and dropping the top chord of the truss, as you can see on the right. And this allows the shower pan to easily be installed in the field without having to add any extensive framing. Now, again, the truss on the right is not a top chord bearing condition. As you can see, it's a bottom chord bearing condition. But again, going back to that piggyback detail, by using a bottom chord bearing condition for the shower pan or shower entry and using top chord bearing trusses out to the exterior of the home, you can really achieve zero entry throughout the entire home. And that's a very, very difficult thing to pull off through any other sort of framing, floor framing methodology. Now, in previous editions of the TPI-1 standard, including the 2014 standard, which is referenced in the code and that I mentioned earlier, the design provisions for top chord bearing trusses were limited to this prescriptive table in the standard, table 7.4-1. This table specified maximum allowable reactions. Now, this table was developed based on testing conducted by TPI members and others in the 1980s. And, they were testing specifically top chord bearing parallel chord trusses, but in limited configurations. Now, this is a little bit of a problem because while this table has provided a reliable design solution for a range of specific top chord bearing configurations, which has really served the truss industry well since its initial publication in 1987. It's great because it offers designers a quick and convenient method for designing top chord bearing trusses. And certainly this remains an option in the 2022 standard as well, but it presents certain limitations for truss designers, including that maximum half-inch gap between the edge of the bearing and the vertical web, which I pointed out a few times before. Also one limitation is the connector plate at the extended chord joint. So that last joint where the top chord extends, it had to be located in a prescribed location without any allowance for normal plate positioning tolerances. Also, there was no variation in strength recognized for different species or grades of lumber. Another limitation is that the design of the connector plate at the top chord joint wasn't really addressed in any way. And so it had to remain consistent, and there was really no consideration or benefit given to using lumber sizes larger than 2x6s, which is really what has limited the application of top chord bearing trusses to 2x3, 2x4, and 2x6 up to this point. So instead of relying on this prescriptive design methodology, the TPI 1 2022 standard now includes a more advanced and comprehensive analytical design methodology. And this is important for building designers to at least have an appreciation for. While they won't have to apply any of these conditions, the truss designer will handle this. It's important to know that these changes have been made, which provide much greater flexibility to the design of top chord bearing trusses going forward. This new approach allows for the consideration of any extended chord bearing conditions, whether it's at the top or bottom chord. And this analytical based design also takes into account various crucial factors, such as the size of the lumber used in the truss, the species and grade of the lumber used in the truss, the distance between the edge of the bearing and the first vertical web. Again, remember, we were talking about up till now with a prescriptive approach that was limited to a maximum of 1/2 inch. There is now a methodology that would allow that gap to extend into a larger gap for particular design elements. There would just have to be accommodations made. This analytical based design also allows for consideration of the placement and size of the connector plate, and also the absence of wane in the extended chord. And again, that's specifically looking at that bearing surface and the contact between the bottom of the top chord and the top of the bearing or support structure. The important part here is by incorporating these elements into the truss design methodology, this approach not only enhances the accuracy of the final truss design, but also allows for greater flexibility and adaptability to different construction scenarios. So the determination of the maximum allowable reaction for an extended chord or top chord bearing truss in the latest edition of ANSI TPI 1 2022 now considers several failure modes in the design process, which again will provide greater flexibility. I'm now going to spend a few minutes quickly walking through each of those 8 failure modes. Again, for a building designer, they don't have to be specifically concerned about any one of these failure modes, but it's important to understand why these failure modes are looked at, and again, how they introduce flexibility into the design of these trusses, which again give building designers greater flexibility. So the first one is compression perpendicular to grain. This check is crucial in preventing the crushing of the chord extension under the design load. Now, this crushing is usually considered a serviceability issue, but it can also be a structural safety issue, as it can trigger other failure modes of the plate and chord, as the crushing causes the wood section to break down. And this is important because the presence of wane in the chord extension significantly affects this check. And when you think about lumber quality currently in the US, there is a significant amount of wane that exists in dimensional lumber produced by lumber mills, which makes a lot of sense. And structurally, there's a lot of allowances for this, but in this particular application, it's important to consider the impact of wane on the bearing location. So ANSI TPI 1 2022 has included a wane factor, or C wane. By strictly prohibiting wane in the extended chord region, so setting C wane as 1.0, a substantial increase in bearing capacity can be achieved. So really what this means is for truss designers and for building designers is that in the past with a prescriptive method, that bearing capacity was fixed. But now, again, every truss is produced as a one-off product. Every one is unique. And as you saw in the fabrication process, the fabricators on the line are able to visually inspect every top chord, bottom chord, and web that goes into a floor truss application. And so the floor truss designer, for example, can set the C wane factor at 1.0, meaning the lumber has 0 wane, and then they can achieve a higher bearing capacity, which may increase the allowable span or impact everything from the required lumber grade or species used in the floor truss or the depth of the floor truss itself. So again, great flexibility just in that one change. Then there's shear in the chord extension. This design provision ensures that the extended chord does not exceed the allowable horizontal shear stress. The good part is it recognizes increased material capacity with smaller wood volume exposed to shear. So in simpler terms, what this means is it guarantees that the lumber does not fail in a horizontal plane through the center of the chord. I think a helpful visual for this type of failure is bending a deck of cards and thinking about how the individual cards slide over each other. This scenario is sort of what you would see in a horizontal shear failure in lumber. Again, if you look at the detail on the left, sort of in that red jaggedy area, that's where you would see that sort of shear in the chord extension. The next is bending in the chord extension itself. So this design provision ensures that the extended chord does not exceed the allowable bending stress. This check, among others, becomes critical when the gap between the edge of the bearing and the first vertical exceeds ½ inch. Again, this is important that this check is now in here because in the past, again, with a prescriptive method, it was maximized at ½ inch. But now truss designers have some flexibility in potentially designing a truss that can exceed that ½ inch maximum gap for various design or construction allowance reasons. The next check is rolling shear. This check focuses on the plate to lumber connection and ensures that the forces in the extended chord joint do not surpass the rolling shear capacity. Now, rolling shear failure occurs when the wood fractures around the connector plate and chunks out a section of the lumber with the teeth remaining embedded in the wood. This is as opposed to a typical tooth holding failure where the plate teeth pull out of the lumber. And while this failure mode is not a common failure mode for wood trusses, it can occur when with a large perpendicular to grain force typical in top chord bearing joints. So it's an important thing to look at. It's important to note that this failure had not previously been considered at all by the TPI-1 standard. But because of recent research and testing by the industry, they were able to incorporate a methodology for considering this kind of, and quantifying this kind of failure mode. Again, being able to consider this kind of failure mode adds additional design flexibility into the top chord bearing truss. The next is tension perpendicular to grain. This design provision ensures the chord does not fracture through its thickness at the edge of the connector plate. This check becomes more critical on extended chord bearing trusses as the plate bite into the chord decreases relative to the chord depth. So again, a very important check to be able to put into the design of top chord bearing trusses, again, because of those bending and tension forces that are going through that joint. The next is connector plate tooth holding or lateral resistance. Similar to the check performed on all the other joints on a truss, this check ensures that the connector plate possesses sufficient tooth holding capacity to withstand the forces exerted at the joint. However, extended chord bearing joints exhibit stress concentrations on the connector plates, necessitating special consideration in the design. So this is an essential check, and again, is facilitated by recent industry testing. And the bottom line, again, is that by adding this check in there, there is greater versatility in how that top chord bearing condition is handled and how that truss can be designed. The next one is steel stress in shear and tension on the connector plate. So this check verifies that the connector plate possesses adequate metal shear and tensile strength to withstand the loads present in the extended chord bearing joint. Again, an important check. And finally, the last check that has been added in the ANSI TPI 1 2022 version of the standard is a check for deflection. So under the 2022 standard, the truss is also going to be evaluated to prevent undesirable deflection in the extended chord region. So even if the joint design satisfies all the other strength checks, localized deflection of the joint may render it unsuitable for use. So this is an important sort of last check. This design check imposes limitations on deflection, including that due to the extended chord. So by considering all of these different failure modes in ANSI TPI 1 2022, the maximum allowable reactions for these top chord bearing or extended chord bearing trusses can more accurately and reliably be determined by the truss designer, which allows for a much greater range of configurations of top chord bearing trusses. And for building designers, this is great news, because it means that this versatile tool that they have in their arsenal can be used in more varied applications going forward. So it'll provide greater versatility and greater value for building designers. And this is particularly important because the truss design, or the component manufacturing industry, is an industry that, as I mentioned very early on, has been producing floor trusses since the 1950s. The connector plate itself was designed, in 1952. So, it's been around nearly since its inception. But the use of floor trusses in buildings has really just taken off in the last 10 years. We've seen significant increases in market share, and we'll talk about that a little bit in just a second. But overall, the specification and use of trusses, whether they be roof trusses or floor trusses, or even wall panels that are produced by the same manufacturer, have all seen significant increases in recent years. And ever since sort of the inflection point of the housing downturn, so say about 2012, as the housing market has steadily increased since then, there has been significant investment in component manufacturing operations. And those investments, which has really taken off significantly just in the last 5 years, has made a significant impact on the manufacturing process, design capabilities of component manufacturers, but also their proliferation across the US. So before I end this presentation, I want to spend just a few minutes sort of talking about the growth of the component manufacturing industry, why it's happened, some of the motivating factors, and also how that impacts building designers today. So when we look at today's component manufacturing operations, offsite construction itself hasn't become a sexy jargon term overnight. It took several years, almost most of this last decade. Personally, how I witnessed this was I've been attending NAHB's International Builders Show for the last 12 years, probably 13 years, really. And, in those early years coming out of 2012, 13, 14, 15, you saw builders talking about how, now that they were seeing a reversal in their fortunes and seeing a steady uptick in their business prospects, they were talking about how do we bring capacity back online. And so for a builder to bring capacity back online, it was really about how do we get more bodies onto the job site to frame up these buildings, install all the MEP infrastructure, and get these houses finished. And so in those early years, there was a significant investment made in trade programs, in marketing and outreach, in trying to bring more young people and others into the industry. And I say that was like 12, 13, 14, 15, because it took several years for, I think, home builders to realize that there had been a dramatic shift in whether it was a sociological shift or just a demographic shift, but a shift nonetheless away from these job site manual labor jobs. And so all this money that they had thrown into those efforts was kind of for naught. They really weren't seeing the kind of uptick that they had experienced in the past of being able to draw people into the industry. And so, as they experienced that, they started thinking about, well, what are our other options? And so they began exploring other offsite solutions. And as builders, from 15 on, talked seriously about, evaluating different offsite solutions, we saw a dramatic uptick in the investment into the fabrication process of today's component manufacturer. And so you saw dramatic leaps in everything from automated material handling equipment, improvements in linear saws. Again, as I showed those videos early on about how floor trusses are fabricated, each one of those webs, both vertical and diagonal webs in the floor trusses, are cut very precisely, and those linear saws are what allow that to happen. Beyond that, automatic jigging systems, particularly for roof trusses, laser-guided systems for the placement of connector plates, both on roof and floor truss systems, automated nail bridgers for wall panels, even robotics like you see here on the screen. All of these advancements have really happened in the last 3 to 5 years. And what that means for building designers is that these framing products have become much more precise. And because of that precision, they're able to accomplish more in the field. And of course, certainly when you think about all the changes that have happened that are reflected in the latest version of the ANSI TPI 1 standard, some of those changes are a result of, again, this increased precision in the manufacturing process that have been borne out in the field and through testing are now reflected in the design software itself. And so it's been a nice cyclical process from that standpoint, and we've seen continuous improvement. And it's not just the improvement in the component manufacturing space, it's been the ongoing reality of job site labor. This chart on the right you see is a recent survey of home builders, and you can see the percent of builders reporting shortages of subcontractors. The top three highest or biggest shortages are really in carpentry and framing crews. So again, builders are really motivated to find solutions, particularly for this area of home construction. They're not finding enough field labor. Even the field labor that they're finding, they're reporting, they sort of lack the training and skill necessary and the experience necessary to continue on traditional framing practices. And when you add in sort of the growing liability and enforcement environment that exists on today's job site, you can understand why builders today are very motivated to find off-site solutions. So why do I bring this up? Well, when you add to that builders and developers are also, and building designers feel this in spades, are looking to control cost, reduce disruptions, and reduce overall construction schedules. And they're looking for things that are not disruptive, that are easy to incorporate with their existing field labor. Time and time again, what they're finding is that one of the best solutions is structural components. Again, roof trusses, floor trusses that we've talked about today, and wall panels. And where that leaves building designers is the more that they can understand what today's component manufacturer can do, the better able they are able to incorporate those elements into their building designs. One other thing I do want to touch upon real quick is just, going back to this scatter plot of the 1,300 component manufacturing locations across the US. Today's building designer, today's builder, today's developer can access this construction methodology anywhere in the country, whether or not they're SPCA members. So what that tends to, particularly if you compare it to some of the other off-site solutions that have been touted in the media recently, those are limited to very small geographic areas in the US, particularly with high population concentrations. So for building designers, if they want to incorporate elements like top chord bearing trusses into their building designs and into their projects, they know they can have the confidence that they can do that today because there's a manufacturer located pretty much anywhere they want to build. And I'll just point this slide out because, when you look at roof truss market share, roof trusses are really I say this with tongue in cheek, but it's really a gateway drug for most builders who are looking at offsite. Again, roof trusses have been around since the 1950s. And so it's not surprising to see many parts of the country are sort of this deep green, meaning that, you can have anywhere above 70% market share penetration for roof trusses. And that, again, is why those number of manufacturing locations are so prolific, again, across most of the United States. But those manufacturers can produce floor trusses just as easily. It takes the same building materials, it takes the same design methodology. It just takes additional space and some additional fabrication equipment. And so for building designers, they already know that most of their building projects utilize roof trusses. Incorporating floor trusses into their projects becomes exceedingly easy. And so hopefully that message comes through clear. In conclusion, whether it's simply changing the depth or configuration of a truss or the strength of the material used in the components fabrication, truss designers have a lot of variables at their disposal that they can adjust to design a floor truss to meet a particular need. Top chord bearing trusses give building designers even greater flexibility when trying to address specific design challenges like fire-rated assemblies or zero-entry homes, or even things like those pocket beams, interior bearings that they don't want to have overtly, hanging down underneath the ceiling diaphragm or something like that. Add to that, recent changes to the ANSI TPI-1 standard increase the design variability possible with top chord bearing trusses. And so this really awesome structural element that has been out there for a long time has become more versatile. And so if there is one thing I hope building designers walk away with from this presentation, it's to take a fresh look at top chord bearing trusses. And how do they do that? Well, the key really is for the building designer to find and work with a component manufacturer and explore together the wide range of possibilities that are there, whether it's with top chord bearing floor trusses or bottom chord bearing trusses, or that piggyback combination of both of them, or it's a roof truss, or it's a wall panel, or it's a combination of all of those three framing elements. But the key is to work with the component manufacturer to find a solution that works best for that building designer's next project. I want to thank you for attending today's webinar. I would love your feedback on how we can improve this presentation for building designer audiences in the field going forward. I have found that soliciting questions in this format can be exceptionally difficult, but I've had some great follow-up conversations with building designers, with truss designers, fabricators, engineers over the period of giving these designer series webinars. So if you'd like to talk, provide any direct feedback, please shoot me an email at the email address below. I'd be happy to give you a call or shoot you an email back and have a conversation.